Evo ga, tu je. Hello, welcome back. Moving on with Veljko Pejovic, assistant professor at University of Ljubljana. He received his PhD in computer science from the University of California, Santa Barbara. From 2015, he's an assistant professor at the Faculty of Computer and Information Science, University of Ljubljana. He's going to present his talk on lightweight deep learning on edge devices.
Thank you, and I would like to thank the organizers for a very nice conference, as always. So my name is Veljko Pejovic. As said, I'm an assistant professor at the University of Ljubljana. Currently, I'm in Lancaster, UK, but this is just a temporary thing, it's just my sabbatical. With my work, with my group at the University of Ljubljana, I develop efficient mobile systems. And today I'm going to present just one slice of our work. I'll be around after the talk if you want to find out more details about other things we are doing or just to chat about what I'm going to present now. So what we advocate for, and we believe is right, is that the AI should be moved more towards the edge, where by the edge I mean mobile phones, I mean IoT devices, any sort of a device which is in your local possession. Why? Well, because the data should stay local, and indeed, users are concerned about the privacy. So the more you keep your algorithms close to the user, the more likely you are to keep the users engaged and less worried about the processing that happens over their data. The other thing is that AI in the cloud is good, it's powerful, but it requires connectivity. It requires, especially if you think of critical applications, say those connected with critical medical devices or with self-driving cars and so on, the connectivity you need for such processing is not always available. And there you risk into getting into really catastrophic effects because the existing infrastructure might not support your service at a given moment. Yet moving the AI to the edge is not straightforward. Main reason being the models that we build, deep learning models that we build for data processing are tending to be larger and larger as we try to compete with the previous generation of models. Here is a rather old picture of the model size in terms of number of parameters and the model performance on a few on certain image recognition tasks, I believe. But what you can see is a general trend for the models to become larger. And the other thing is that devices that you have on the edge are rather heterogeneous, and they are powered by batteries. They may or may not have the sufficient memory that you need for keeping all, say, the activations of a certain layer of a neural network in memory. So they might need to do more or less of the data transfer, and they might consequently lead to performance in terms of the processing time, which is suboptimal. So here, again, another borrowed graph, a rather ugly one, that shows how the latency of image recognition from a picture, from a frame, goes up as you increase the image dimension, and consequently, the number of frames that you can process per second goes down. And what's really important to get from this picture is that this reduction in performance as you increase the input size is not uniform across all devices. And imagine when you put your mobile application on Google Play, you have no idea what is the diversity of the devices on which this app will run. Therefore, it might happen that your app is consumed by users who have actually rather cheap phones that cannot cope with the algorithm that you designed, with the network that you designed. So, OK, we can just wait for some time like we did before, and things will clear up. So with every new generation, we get more processing power on the phone, and the algorithms will run faster. I claim that this is not going to continue much longer. So there's a law, more or less an observation, called Denard scaling. And it says that for the same area of the chip, you need the same amount of power to have transistors on this chip running, irrespective of how many transistors you pack into this area. And this law used to hold for a number of years and recently started breaking down. So basically, you cannot count on the next generation of the phones, the next generation of chips, cramming more transistors in and still needing the same amount of power for its operation. Instead, as you pack more transistors in, you will need more power for the phone. This with mobile phones is very critical because you cannot simply expand the battery. The batteries need to be small if you want the phone to be mobile. This is solved in traditional server-based computing by going multi-core. Again, on a phone or a limited area IoT device, you cannot pack more cores because that expands the area. So my pessimistic view is that phones are not going to get much better in the future. And we will need more energy for computation and cooling of devices if we continue down the business as usual path. Instead, what we advocate is, let's just reduce the amount of computation. Do we really need all the computing at all times? And here I'm going to show just one example. It's a use case that we experimented with. It's not from the area of AI, but the general philosophy holds. And the idea is that in certain contexts, you might require high quality of service, high accuracy, whatever you want to call it, from your application. Say this is a video streaming or video calling application. And then say you have a meeting, you're at your desk, and there are some important charts being shown on this call. In that case, you might want high accuracy or high quality of service, whereas in some other example, say you're on public transport and you're already kind of limited in terms of what you can consume from the screen, you might be fine with slightly reduced accuracy of the picture, for example. And finally, there might be cases where you're really paying very little attention on what's going on. And in this case, you might require a lower quality of, say, picture. Interestingly, in many application areas, this accuracy, quality of service metric correlates with the resource usage for the computation that leads to the desired quality of the result. Current mobile applications always aim for this point. They essentially try to give you the highest possible accuracy, so they try to use the most of the device's resources. If, on the other hand, we could identify the minimum that the user is satisfied with, we could reduce the resource usage in our computation and stop paying this accuracy tax. This might be tax in, say, the time to compute the result, or the energy, the battery energy that's needed for computing the result. So this is the general philosophy that we work on at the University of Ljubljana. And what I'm going to talk about next is just one particular implementation of this philosophy in the area of mobile deep learning. Before we go down the implementation, let's just first identify certain opportunities for what we called approximate mobile computing in the previous slide. So one is, and I actually want these to be more like actionable guidelines for any mobile developers in the room. When building your apps, think about where you can save computation and energy, and maybe these will help you identify such use cases. So one would be when the computed result quality exceeds the limits of human perception or attention. The example that works for me is lossless compression of audio. Like, I cannot hear the difference between high-quality MP3 and FLAC, for example. There are often occasions where the user's interests are such that they don't care about the higher quality. Say, if the gist of the humorous video is the action on the video, not the quality of the video. When preserving resources is more important than the high result quality. So, for example, when navigating, perhaps you don't need to give me the most appropriate route, but a route that will get me there without draining my battery. Cases that are more related to the topic of this conference, and AI in particular, are when the inputs are inherently noisy, and that often happens. And even these deep learning models are often such that really there's a lot of space for approximation. And finally, what I'm going to harness a lot in this talk is when the inputs are inherently easy to process. Now, the catch is, how do you know that an input is easy to process and you can reduce the amount of computation? This we'll see further in the slides. So with that in mind, we decided to implement something that will help any developer that uses mobile deep learning to optimize their network, so to use context-aware approximation. So the goal would be to let the developer use this even if they don't know anything about approximate computing, to use this even if they are not data scientists, so they just have a network. Maybe they downloaded the network somewhere online and they just want to use it in their app. And that the approximation is dynamic, so that if they want a network at one point to be accurate, perfectly accurate as much as possible, they should be allowed to do that. If they want the network to save energy as much as possible, they should be allowed to do that. And they should be able to switch between these operational points at runtime. So for that, we built Mobiprox. Mobiprox is a whole framework, compiler suite for programming approximate deep learning mobile apps. It consists of a few parts, where the key part is implementing support for these operations, tensor operations within the neural network in the approximate way. And then imagine that your neural network consists of multiple layers, where each layer could be independently approximated in a certain way. We'll talk more about these ways later. So let this be a fraction of a neural network. In this case, it has 3 convolutional layers. Say I decide to approximate the first layer. So it's here depicted with this dashed lines within the convolution. That will give me a network which is of the same architecture, but has this operation approximated, so the result will be similar, but probably not the same as the result of the first unapproximated network when a certain input is put in. I might decide to approximate another layer, and I might use a different kind of an approximation for this. Or I might decide to approximate 2 layers, for example, the first and the last layer. Now, the issue is there are many, many ways I can approximate a network of, say, 20 layers if I have, say, 5 approximation techniques. How do I know what is the quality of the output that I will get if I approximate in a certain way? Well, that I will have to profile. I'll have to go and measure the quality of service loss, say the accuracy loss on a certain validation set of my network, if that network is ran without any approximations, if just one layer is approximated, if some other layer is approximated, or if multiple layers are approximated. And then I should explore this space, go through as many combinations of approximations as possible. I'll call one of these pictures approximate configuration. So I'll go through as many as possible approximate configurations, and I should find a Pareto front. Basically, I should find approximate configurations that give me the best trade-off between speed up, so they will run faster because they're approximated, and quality of service. They will lose as little quality as possible. And as you can see in this very simplified picture, some approximate configurations simply don't make sense. If you have an approximate configuration that is better, both in terms of the speed up or and the quality of service loss, than some other combination, then there's no need for this for this dominated configuration to be taken into account at all, right? I mean, it's slower and it gives you worse result. So once we identify these configurations, so the ways you can approximate a neural network, and we identify the best, the most promising, then we should develop algorithms that allow us to somehow intelligently jump across these configurations in the Pareto front. So to implement these tensor operations on the mobile phone, we had to dig a bit deeper into Android stack. And we decided to implement three approximate computing techniques. One is called quantization. That means simply that instead of computing with 32-bit words, we compute with 16-bit words, so that runs faster, and that's already supported by mobile hardware, such as mobile GPUs. The second technique is called filter sampling. So in convolutional neural networks, you have a filter that goes over an image, and it convolves the filter with the image. But if you decide to simply ignore certain patches in the filter, you get a much faster computation. You get an approximate result, because obviously you're not doing all the computation. Yet in many situations, it works quite well. And we implemented also the perforated convolution. So here, we are not going to perforate the filter stays the same, but instead of going over each pixel, we simply decide to jump over certain rows or columns when we convolve. And then we can decide to skip more or less of these rows. So achieve more or less approximate computing. The rest we just interpolate. To implement this, so to implement these operations on the mobile in Android, you have to go and find where the convolution, where the tensor operations are implemented, and then re-implement them to support approximation. This is not easy, and it didn't work after many tries. We finally managed to do it by writing pretty much all of the stuff ourselves using CLBlast library, if you're familiar with that, basically OpenCL implementation of all of these operations so that a GPU that's on the phone can run these in an approximate way. Then, so finally, we have a means to run an approximate network on a mobile phone. Now, how to identify those configurations that are promising. Now, for that, we have to go over many configurations, because if I just presented 3 techniques, each of these 3 techniques has 10 possible flavors. Sorry, I presented 4 if you count row perforation and column perforation as separate techniques. So 4 techniques, say each technique has 10 possible ways. So you have 40 possible approximation techniques, and you have, say, 20 layers in a network. So you have 20 to the power of 4 combinations, many. So you have somehow to figure out what are the best approximate configurations. For that, we relied on the existing tools called ApproxTuner and ApproxHPVM. I'm not going to go into details of these, basically heuristics for finding the Pareto front of approximate configurations. By the way, on this work, we collaborate with people who actually work on approximate compilers from the University of Illinois Urbana-Champaign. If you heard of LLVM compiler, the group that invented that. And what I show here is a particular example of a network that we profile using this tool called Approxtuner to find the most appropriate approximate configurations. So each of these points is the same neural network, just approximated in a slightly different way, and then ran over the validation set to calculate the quality of service loss and to calculate the speed up. And this was done on the cluster. This is very computationally intensive. You do this on the cluster, it runs for an hour, and then you get this picture. And then you can identify the most promising techniques. When you try these approximate configurations on the phone, it doesn't work. Well, it works to an extent. So this is what you get when you run these, just the approximate configurations from the Pareto front on the phone. You get a much lower speed up, and the ordering might not be the same as you had in the original calculation on the server. So we had to develop a profiler that works with the phone as well. So to summarize the whole process, say you're a mobile developer, and you found a network or you trained a network that suits your needs, and you want to optimize it so that it runs on the mobile efficiently. You do the tuning using Approxtuner, so you get this list of possible approximate configurations. You then do profiling on Android, so you connect an Android device. It runs selected configurations, so you can get the actual speed up and quality of service loss that you can expect on the mobile. And then we provide the supporting infrastructure so that everything is packed, so it's accessible through Java, through JNI, so that your Java/Kotlin app can use this network, and everything is compiled together in an APK that you can push to the user. Then your program, your Java app, can control the amount of approximation, so it can switch between different approximate configurations at runtime. Great. How to switch? What would be a good strategy? Any strategy can be implemented, really. Some that come to my mind are, say, if a user, say you have an app that does activity tracking of a user, it might count steps and maybe the amount of time spent walking, sitting, and so on. It doesn't have to be very accurate in that mode. But then when a user starts exercising, maybe it should be more accurate. So maybe the same network should just switch to a more approximate configuration when the user is not exercising, and then switch to an accurate configuration when the user is exercising. It could be that the whole thing becomes more approximate when the user gets, when the device gets low on energy. So when the battery is running low, you switch to approximation, just trying to save the resources. You can even think of a business strategy. Say, for premium users in this situation, prioritize battery saving, or prioritize energy, or accuracy, or whatever you want. The one that we found kind of to be universal and we wanted to experiment with is minimize energy usage without sacrificing the inference accuracy. And this comes from our insight that in many situations, you get inputs that are, what I said, easy to compute. And there's no need for them to run through the unapproximated network, so through a perfectly accurate network. And to do this sort of an approximation, we developed an algorithm, adaptation algorithm, that relies on the softmax confidence. So in neural networks used for classification, when you put the input in, you get the output out, which tells you sort of the confidence of a network that the input belongs to a certain class. Say, this accelerometer input belongs to class running, so the user is running. And there's a certain confidence associated with that. What we noticed is that the network becomes, the confidence that the network outputs is often correlated with the accuracy of the network. So the network starts making mistakes when it's less confident. And we, for different approximate configurations, profiled where the limits are, basically, when it starts being less confident and it starts making mistakes, but we also kind of profiled when is it that it starts becoming very confident and there's no need for us to be that accurate anymore. We can jump to a more approximate configuration and still get an accurate result. So our algorithm basically works like this. You start with, say, an approximate configuration, this one, that comes with two thresholds. One is a red one, below which you can say that the network is not confident anymore. You should lower the approximation. You should make it more precise. Yes, lower the approximation. Or the blue one, the network is too confident. You can try to approximate more. So say your inferences come in, and for each inference, you calculate the softmax confidence. Once the softmax confidence goes into red, you try to approximate less. So use a more accurate configuration. And then the softmax confidence will change, but it might still be inaccurate. So you try with even less approximate. So this is like a perfectly accurate network. And then as long as you operate between these two thresholds, you keep it as is. Once it becomes overly confident, you can go and try to approximate more. So this simple algorithm actually got us to very interesting results. So we tried with human activity recognition. We fitted volunteers with devices that measured acceleration. And then we did on-device activity inference with 6 prescribed activities. So sitting, walking upstairs, running, and so on. And for pretty much all the users, so the blue lines are the accuracy and the battery consumption when no approximation is employed. And the orange ones are when the approximation, this dynamic approximation is employed. We get reduced power consumption on the device, and we get almost the same accuracy. So overall, we got 2% accuracy loss, and we saved 15% of the energy. And we also noticed that certain classes are very easy to approximate. So lying, for example, I'm not going to explain this graph, but basically what you get from it is that lying is perfectly classified even with a very approximate network, whereas, for example, walking upstairs is not. Like if you try to use a very approximated network when the user is walking up the stairs, you get a lot of errors. So that's also something to keep in mind. Maybe a network is good in certain situations, approximate network is good in certain situations, but not in others. Exactly what I showed in this slide with the philosophy of approximate computing. And the second example that we programmed is the spoken keyword recognition. So trying to recognize from microphone recordings keywords. This is very important because most of these applications have to run at all times. So in the Internet of Things, home automation, they have to run all the time and then recognize when you say, turn the lights on, or so on. And our assumption here is that in certain contexts, the noise will impair the ability of the network to work well. And you need a more accurate network, whereas when the noise is low, you can reduce the accuracy and reduce the precision, to say, of the network and use approximate version of the network. And we actually ran this. There are more details in the paper, and we got 0% accuracy loss. So there's a lot of room for improvement, 15% energy savings, just by trying to adapt to the level of noise in the space. So this was done the least by me, most by the people listed here. Some of them students, some of them postdocs in the lab. There are some papers here if you want to learn more, but I'm available if you want to chat. We also have the code on GitLab. It's extremely difficult to use, but I'm willing to dedicate some of my time to help you if you're willing to try it out. Thank you very much, and if you have any questions.
They all can't wait for the cocktail party, so.
All right.
Just a minute. I see someone that has a question.
Okay.
So the question is how to use it. Do you have any tutorials or examples there?
We have two singularity containers that you need. So one is to do the tuning. So you take your network, and there's a place where you can put it in the code, and then you need a cluster to run it on, so you get these approximate configurations calculated. And then we have another container for on-device profiling. So in the next step, you need to connect your Android phone somewhere, so you get profiling on the phone. And then you need to put this in the application. We don't have, we are working actually on a step-by-step user manual to say, but feel free to contact me. I'll try to help if you have a use case. We can talk about it.
Yeah, thank you. Thank you.
One more. There's
Oh, there's one more. Okay.
Hi, this is maybe more like idea than the question, but could you use this to do get rid of overfitting? And another thing is, could you use this to make explainable neural networks? Maybe this is more for discussion, so you can just answer yes or no, and we can discuss
That's a good question. I believe that approximation is indeed a way to make a network more generalizable in certain situations, and that has been shown before. It's difficult to quantify and say when this is possible. The explainable AI, I haven't thought about that, to be honest. But if you have an idea, we can chat more about that. Okay, thank you.